might learn some new things here, but it's also about just having fun. But you will see in the next hour, and you've probably already seen it here at the front. Before I get the question, no, I unfortunately don't work for Lego. However, despite spending a lot of free time on this project, I also got my manager to give me some company time for it, so I at least work for a nice company. Of course, you need a disclaimer. Unfortunately, between traveling from Krakow to Amsterdam to here, most of the Lego broke, so I had to fix it yesterday evening. But I mean, Lego is quite flexible, and you can just build it up again, so that's a good thing. However, some Raspberry Pis unfortunately died beyond repair, but I mean, there are enough of them. So this is a bit of the content for today. I put questions at the end, but if you have any questions, feel free to just interrupt me and I'll try and answer them immediately. But first, why did we do this? I mean, some of the reasons are probably obvious, to have a bit of fun. But what we also wanted to try was if we could use languages and tools that we used to build big applications for big customers like financial institutions, if we could use those same languages and tools on IoT hardware like a Raspberry Pi. So to run Java and Akka and stuff like that on a Raspberry Pi. Because nowadays IoT, it's getting more and more popular. You probably noticed it if you came out of your house in the last couple of years. But so we also wanted to see, like, hey, man, can we do with our current knowledge, can we easily get into the IoT business without having to learn a new C language or whatever? So that was also one of the things. And we also, it's a lot more fun to make something visible with, for instance, Raspberry Pis and Lego, instead of just building Hello World in a new framework. Of course, we could have built Hello World, and yeah, we could have learned probably more or less the same lessons as we have learned now, but it's a lot less fun. And if you build Hello World, then probably after you typed Hello World, you stop programming any further because it's not really fun. But with this, I mean, you can keep on adding sensors and stuff, and it keeps on being fun. And the cool thing is, it's also easy with this kind of stuff to explain concepts to a bit less technical people. For instance, if I tell to my wife that I'm using event-driven architectures where a message M is sent from system X to system Y, then probably she would have stopped listening at event-driven or somewhere around that. And that's not her fault. I mean, she has no technical background, and we speak in some alien dialect. But when I tell her, okay, we do event-driven architecture, so I send a message to my train, and the message says to play a song, and then the song starts playing. I mean, that's understandable for probably everybody. And you more or less say the same thing, just in some simpler words and with a nice example. So we had some different reasons to doing this. But be aware, after you start things like this, it can grow out of hand. This is just a small part. In the end, more or less, my complete living room was filled with Lego, which is fun, except if you have some small children that are too small to play with Lego, then it's a bit of a challenge to be quick enough to clean everything up before they enter the room. So getting started. First, let me ask you, who of you already have a Raspberry Pi? And please keep your hands in the air if it's collecting dust on a shelf. Okay, so most of you I see already have the Raspberry Pi, so that will save you around $25 or something like that. So you could use the one that's collecting dust or that you now use for your home theater or whatever. And build this with it, because the only basic ingredients you need is a Wi-Fi dongle, a USB battery pack, and an infrared transmitter. And maybe you even have a Wi-Fi dongle, because it's just a USB Wi-Fi dongle. Maybe you already have a USB battery pack, then it's even cheaper, because the infrared transmitter is like $1 or $2. So this is mainly the basic ingredients if you go shopping for something like this. But you can go a bit further, of course. And what we did with this train was we added camera to it. So this is the Raspberry Pi camera, which can stream full HD video, so that we could live watch video streams from the front of the train. For instance, if I'm at work, I can watch this stuff on my cell phone. Of course, only during lunch breaks. And underneath here, there's a RFID reader. So we have RFID cards around the track. I will go into it later. And with that, we can detect the position on the track. And we have a speaker to play train sounds, because, I mean, what's a train without train sounds? yeah, one thing that where have been looking for was like, okay, which kind of hardware are we going to use? And we started this project around 1.5 years ago. So then the Raspberry Pi Zero was not really available yet. So we opted for the Raspberry Pi A+. It's less powerful than the Raspberry Pi 2. So if you want to do heavy calculations, it will take a bit longer. But it's also a lot smaller, and it consumes a lot less power. So if you're running on a battery pack, with this setup, you can go a lot longer. And we've been looking into charging automatically through induction the Lego trains at a fixed point on track. So if you manage that, then you can even use the more heavy Raspberry Pis. And you can still drive the train 24/7 around your track. And now you have the Raspberry Pi Zero, so now we could also build it with the Raspberry Pi Zero. And the first model of the Zero, it didn't have the camera connection. So for instance, for the Blue Train, we couldn't build that with the Raspberry Pi Zero because the connection wasn't there, or we had to use like an alternative camera with USB or something else. But now the new upgraded Raspberry Pi Zero also has a camera connection. So in fact, we could replace our setup with Raspberry Pi Zeros and even save some more time and some more power consumption. So that would be a nice upgrade in the future for us. We also looked at like Odroid, but I didn't really get them stable. They were crashing all the time. Nice thing of Raspberry Pi is that there is a big community, so if you have any crashes or whatever, there's always somebody else that had the same problem, so you probably can find an answer, or at least you're not the only one with the problem, so you can feel more comfortable. But with Odroid, it was a bit hard. So in the end, I just decided to use Raspberry Pi, the new 2 model, for some applications in our setup. So architecture. We started more or less with this as an architecture where LTCC, of course, stands for the Lego Train Control Center. You probably already guessed that. There was an Angular front end, or still is an Angular front end, with a Java application behind it, which was running on my laptop. And then we had a device control, which is running on the Raspberry Pis on the trains. We had a switch control, which was running on the Raspberry Pi for the switches. And underneath, they used some libraries in C or Python, which we modified a bit. It's a bit harder to write it directly in Java or Scala. And this was already available, so when we started, we just started using this. And we used something to control the camera. And this all used REST, so you made REST calls from Angular to the Java application. Of course, this symbol is REST. And to the different Raspberry Pis, there was also a REST interface, so it was all REST calls around. Worked all like a charm. We had it all up and running, and then we started doing a bit of Scala and Akka courses, and we're like, okay, Akka, it looks really cool, but yeah, we want to try a bit with it. And again, I mean, we could have written Hello World on my laptop, or even run a couple of Hello Worlds next to each other and on my laptop, but we were like, okay, let's just rebuild everything from scratch. So we still need a bit of a REST endpoint because you cannot access actors directly from a non-Akka system like Angular. So we have REST endpoints here for the front end, but between the Raspberry Pi and my laptop and this Raspberry Pi, all the communication is done with remote actors. We'll show you a bit more about that in a minute. And here we still have a bit of a REST endpoint because the infrared library works, or not the infrared, the RFID library works with REST calls. You can define an RFID tag that has a unique ID, and then you can say, okay, call this URL, and therefore we still need a bit of a REST endpoint there. But most of it is replaced with remote actors. On the hardware side, we started with basically doing everything wireless because it's cool. You don't need to attach any cables and that kind of stuff. Worked like a charm at home at my company, and then I think the first time we did it at a bigger conference was like Devox in Belgium or something like that. And then it hardly worked because you have all the network that is interfering with your network. All the companies have their own router at the booth, so that's quite tricky. So in the end, we decided, okay, let's make sure that everything that can be wired, like we have the camera that is sitting there at the top of the box. This one, it isn't moving, so we could wire it. The laptop isn't moving, so we also wired that to make sure that the number of calls was limited and we could get a smooth running system. Of course, we didn't put any cables on the trains because it would look a bit silly if we had cables running after the trains. And yeah, how does it work? Everything connects through a router with this USB dongle that is put in the Raspberry Pi, which is laying on the train, where the device control program is running. The device control program is using Lyric, the Linux infrared framework, and an infrared transmitter to send infrared signals to this infrared receiver of Lego. So we didn't have to fiddle with Lego, we didn't have to break anything. It was just more or less out of the box. We could use it with some modifications on our side. Originally, I mean, I don't know how young you all are, but when I had Lego trains before, they got power through the rails and everything. But nowadays, they just have batteries inside them. And it works the same as this Wally. So it has some batteries in the belly, some engines in the back. And this is the infrared receiver. And then you have a remote control like this one. They have some different models. And you can run around with them. So this is more or less how the trains work by default. Which is cool for a while, but I mean, infrared isn't working pretty well over larger distances. When I ran the train from my living room to my kitchen, which isn't really big, it's just an apartment, I couldn't stop it anymore, and the train just crashed into the kitchen. Which is fun, but I mean, if it happens every time, it will take you a lot of time to fix everything. So with our new setup, with the infrared and the USB dongle, we practically have reach everywhere. Everywhere in my house, I can reach the trains. And the cool fact is that with infrared from Lego, you only have like 8 channels, so you can control 8 trains. With this, I can control as many trains as my Wi-Fi router can accept. So then I can control even more stuff. Who doesn't want that? Sound? Yeah, quite simple. We just had a speaker with normal output, which you can see at the bottom. And we just use MPEG 123, which is a Linux MP3 player, to play MP3s that are located on the SD card in the train. We had some RFID cards, like I told you, to determine the position. So, for instance, this card is mapped to a cow. This dongle is mapped to the crossing. This one is mapped to the station, and this to the car. So that way we can determine where our train is on the track. For instance, if the camera isn't working and I'm at work again during lunch break playing with my trains, then at least I know where they are. By the way, camera is also really nice to scare away kids or cats or burglars. Or that's also an option you have with a setup like this. It can be used for multiple purposes. Camera. The camera is actually quite a nice full HD camera that works quite well. The only disadvantage is that it's a bit hard to stream full HD images from a Raspberry Pi to a laptop in good quality. You either have the option to just have a couple of seconds delay, which is not really acceptable because in a couple of seconds the train is already run around the track again. Or the other option is to use like proprietary protocols or some solutions that only work on, for instance, VLC or only in Chrome or only in Firefox. So it was a bit hard, and I actually searched quite a while to find a nice solution without delay, which would work in more or less most browsers. And in the end, I found this little tool, the RPI Cam Control. If you want to do anything with Raspberry Pi cameras, really have a look at this one. It's just sort of a web application that you can install on your Raspberry Pi. You can completely configure it. It even has motion detection and stuff like that built in. And the cool thing is this doesn't stream video, it just refreshes pictures. So it just takes a lot of pictures, and on your laptop the pictures are just refreshed really quickly, like once every 10 milliseconds. So if you look at it, you probably won't notice it, or if you have really good eyes, maybe you can notice it, but I doubt. And that way you don't have much delay in it. So it's almost completely responsive in that fact. So it's a nice solution. We also made some switches. If you're a bit older, I mean, they still had automated switches by Lego. Nowadays, they don't have them anymore. So what we did was we used some servos, which we, and a Raspberry Pi board with a Raspberry Pi servo controller board, because a Raspberry Pi itself can only power, I believe, 1 servo at a time. And with this board, we could power 4 of them with an extra adapter because they consume quite some power. And then we just use paper clips to more or less bend the lever here so that you go either straight or you bend. And these paper clips are probably the most expensive paper clips in the world. We spent, I think, a morning with 3 or 4 colleagues bending them. They need to be the exact same length because else they don't work. either won't close or won't open. So that was a bit annoying and a bit expensive, but after it works, it's a cool feature. One cool thing about this is I've seen other setups which were built with Lego, for instance, with Mindstorms or other solutions to bend the track switches. But most of them, they have to fiddle with some tooling to get some stuff out of the rails because it won't go smoothly. So they just use some heavy equipment to more or less mess with the Lego trains. If you ever plan on doing that, don't tell it on Lego forums because people there will get really mad at you. They don't like it when you mess with their Lego. So okay, we were like, okay, trains is really cool. But then I saw this one, a ferris wheel, and I was like, oh man, that's maybe even cooler. So okay, how can we automate that? And in fact, it's quite easy. What you can see here is that it has the same infrared receiver, more or less the same engine as the one that's in Wally, and the same battery pack. So I could use the exact same Raspberry Pi with the exact same software as I used for the trains to control this ferris wheel. So it was actually quite easy to set up. So in fact, everything that Lego built with engines and infrared, it's quite easily controllable. Once you have got one up and running, the rest is a piece of cake. Yeah, so then we were like, okay, what can we add more? And I mean, if you do IoT, you need to do something with LEDs. And I sort of skipped that phase. I started with infrared transmitters and infrared receivers. So I had something missing in my life. So I was, okay, we need to do something with LEDs. But controlling an LED with a Raspberry Pi feels like a bit overkill. I mean, you can control probably millions with one Raspberry Pi. So we were looking like, what other kind of embedded devices do you have? And we stumbled upon this one. This is a Particle Photon. Nice thing of that, the nice thing about it is that if you buy it, it has a Wi-Fi chip on board, and it's only like 20, 25 bucks. And you can just you put it on, and then with your cell phone you connect, or with your smartphone, you connect to it, you enter your Wi-Fi credentials and information, and then that photon will connect to the cloud. And then in the cloud you have an IDE. So this is the IDE more or less, and you can just put your code in here, and here you can select which photon you more or less want to flash, because you just put the software on that particular photon. I didn't choose the names, they were chosen automatically. So that way you can just upgrade your photon with a new version of your library. Code is the same more or less as with an Arduino, so if you know Arduino you can use this quite easily as well. And then the cool thing is you can just do a REST call from your laptop through the cloud to the photon. And that's all without having to write extra code. It's just by, it isn't visible here, but there are just method names, and based on the method name you can just do a REST call to it. And that's in fact quite easy to set up. You don't have to do anything for it. And this cloud is even used by other vendors that built it. So if you're interested in it, have a look at it. Unfortunately, it doesn't run Java or anything because it's really a low power device, but it's a cool thing to work with. But of course, I think you're all waiting for some demoing. So let's hope it works. I mean, I always heard from other speakers that demos are the easy part of the presentation. So I was like, okay, then we'll add some other Raspberry Pis and some more software to it. So now what you can see is this is the manual mode. And the LEDs, they display the speed of the train, or they should display it. I think I see something moving. So like 3 dots means it's a speed of 3. If it goes clockwise, the train is moving clockwise. If it goes backwards, it goes backwards. You will probably get it. So hopefully it goes backwards now. So that way we can just play around. And of course we have some music. Let's see if we can hear it. Always helpful when you want to scare somebody. And at the bottom here, you can see what the RFID is, where the blue train was located last. So I hoped it would display car, but it didn't pick it up. Bicycle. So the thing with RFID is if you have like a cheap one and you go either too fast or the distance between the reader and the card is too high, then it will miss it. So this is a nice solution if you don't go too quickly and don't want to spend too much money. But if you go too quickly, it will probably miss a few of the RFID tags. But for our case, that was perfectly fine. Other than that, we made like an autopilot. So we had different kinds of autopilot. Like we could just send a few commands. So now the train will first move at speed 3 for 3 seconds, then it will stop for 3 seconds, and then it will play a sound. Quite simple. The commands are executed on the train, so I could even shut down my laptop and it would just keep on running. But I mean, this is quite simple, and you probably want something a bit more advanced than this. So what we can also do is we can do location-based commands. Give me a minute to enter some. So what happens here is that if the blue train is at the bicycle, then the white train will start moving at speed -4. And what the rest is doing, you probably can figure out yourself while I'm trying to type. What didn't we have? Something like that. So now the white train is programmed more or less. So now we can start moving the... Of course, the blue train was already at the cows, so the white train is now already moving at speed 3, as you can see here. But if you now start moving the blue train, then hopefully the white train will do something else in a moment. Or not. So now it's moving backwards. So this way you can completely program it. We could do the same with the Ferris wheel. We could even tell the blue train that if the blue train would reach the bicycle, that it would have to stop or something else. So you can completely program it so it can react on each other. But for now, let's stop that. Okay, so we had lots of fun, but we also wanted to do, of course, a bit of learning on the job, more or less. So we also investigated how Akka actors work. And this is, in fact, the new implementation that's now running on the trains. For those of you that haven't seen actors before, it's really simple. You just extend an actor class, and you define a receive method. In this case, just everything that's being received is just printed out. Then we say, OK, we want an actor system. And from that actor system, we say, OK, we want a worker actor. And the worker actor is this one. Once we have a reference to that actor, we can just send messages to it. And sending messages is just done by the exclamation mark. So here we just sent the hello conference string to the worker actor ref, which will end up here, and it will be printed. Really simple. In real world, of course, you don't want to send strings around, but this is just to get a feeling for it. And this is for using local actors. So within one JVM, if you want to do communication within one JVM. And the cool thing is you also have remote actors. And remote actors are actors that run on different JVMs. And maybe those JVMs run on your laptop, or maybe the JVMs run on a Raspberry Pi and your laptop. And you communicate between those two JVMs with remote actors. And the cool thing is you don't have to change a lot for that. Here we more or less say, OK, we want a worker actor. And here we say we want a remote worker actor, where we specify like the actor system, the IP address, and the port, and the name of the actor. And of course, you could, if you do it nicely, you put this in configuration files and abstract it away. But just for the sake of the example, I just made it like this. But it's just a really small change that you need to do. And then you can just call the same actor remotely on another JVM. So you don't need to create REST interfaces or whatever. It's just you call the same stuff, and you can do exactly the same. You send the same commands to it. If it is locally or remote, it doesn't matter. You need some configuration for it, but this is more or less just copy-pasting. Maybe you want to change the host name or the port, but the rest is just standard configuration. There is one thing to keep in mind, however. If you send messages back and forth, you probably don't use strings, because that's quite a bad practice. So you probably use something, some case classes or whatever, to send your messages around. So you send the message then from actor 1 on the one JVM to another actor on another JVM. such as, for instance, the play message that makes sure that a song is being played on my Raspberry Pi. You can implement that in a couple of ways. You could implement that play message in both JVMs, but that's duplicate code across projects. So what we did in the end was we just made like a small library, which is like the protocol which defines the messages that go back and forth between JVMs. And it's quite simple. It just looks like this. There is one case class to play something, and there is a case class to request a list of MP3s that are located on the Raspberry. And then we can simply say, okay, from that package name, which is the library that we include with the message protocol I showed you in the slide before, I want to have the music service message, and I want to play a file. So that way you can easily send messages around. So that works like a charm. So what's then the difference between HTTP versus remote actors? I think it's much more natural programming if you use remote actors. You don't have to include any Jersey stuff or whatever, or add extra annotations if you want to make something remotely available. So you can just focus on your business logic instead of some technical stuff that you need to do to make stuff available to another JVM. So for me, it was a lot nicer. And there are some more advantage of Akka that it's concurrent on default, has a built-in load balancer, circuit breaker, and stuff like that. So there are some more advantages of it. But of course, HTTP also has some advantages. It's more independent of technology. I mean, if you call actors from Akka, you cannot just call a .NET Akka actor. The serializing is different, so you're more or less bound to the same ecosystem. You cannot go further than that. So that's why I made REST endpoints for the Angular code to reach into the actor system that we have. And yeah, a lot of people are saying that using HTTP, using JSON, it's more loosely coupled. You can add fields, and you don't have to change both sides of the application. You can just change the server or just the client. And of course, in theory, that's true, but in practice, I've seen that most of the times when you change one side, you need to change the other side as well. So I don't know if that's a big advantage. So I didn't really have good facts why I could convince you to use Akka. So I was like, okay, can I find some hard numbers? Because most people are looking for hard numbers to be convinced. And so first I looked at, okay, what's the size of the artifacts when we build something? So a fat jar just contains all the dependencies that we have. And with local actors, it's like 8 megabytes. With remote actors, it's around 12. If we're using Akka HTTP, you already have like 10 megabytes extra. As a comparison, Spring Boot is around 13 megabytes. So it's still not, compared to Spring Boot, it's not a really big advantage. But so then we were like, okay, let's do some performance testing. And we started using Gatling. If you ever want to do some performance testing, I advise you to have a look into it. For myself, I found it a lot more easier to pick up and get started than, for instance, JMeter, which I've used in the past. And it just uses a Scala DSL. So in this case, we have a scenario which is repeated 100 times, which will just do a get on this URL, and it will check if it gets a OK back at 200. And then it will pause, and then it will do the same loop again. This is optional, so we did one test run with a pause and one test run where we just kept on firing requests. We have 1,000 users that are ramped up in 10 seconds, and also that's also varied. So we started with less users, but I will show you in the results. So this is all you need to do more or less hello world testing with Gatling. And we made 2 different setups. Where everything to the left, here it's all the same, the top scenario and the bottom scenario. The difference is over here. In this one, we do an Akka HTTP call to an Akka HTTP call. This is another JVM. Then that one. And with this, we do a remote actor call to another JVM. So we try to make sure that we could measure the exact difference between those two. And we tried not to fiddle too much with results and not to improve certain points for one framework and not improve it for another framework. But I have to say that for Spring Boot, we had to improve some stuff because else the default REST template, which just had HTTP request, has quite a bad adapter, so we had to change it for an Apache adapter, and that worked a lot better. But that's more or less the only change we made for this setup. So here you can see for 50 users what the response time was in milliseconds, the mean response time. Green is Akka HTTP, and blue is remote actors. So you can see remote actors, they're fairly winning in this slide. So that's a good result. In this slide, it's the same. Maybe you notice this one, this is like a lot higher than the rest. That was a bit of a measurement error. So I did every test 3 times and just took the average of the 3 results. And in this case, one of the results was a lot higher than the other 2. But I opted to just keep the results in, because else I would start fiddling a lot with results, and I don't like to mess with it, because don't trust results you didn't falsify it yourself.
Why with 500, the blue one is always higher than 51?
Yeah, the test we did showed that it differs a bit. So Akka seems to be a lot better than HTTP on higher load, so with higher numbers. And with lower numbers, the difference is a lot smaller, or even REST is faster than remote actors. Why it's higher here than here? It can also be a measurement error. So it's quite close, the numbers. So
Also before, it was like before.
yeah, I don't know exactly. We didn't investigate it that deeply, but we've seen some changes in the results depending on how much load you put on it. If it's a low load application, then probably REST will give you quicker response times. If it's a high load application, then probably remote actors are quicker. In between, it's a bit vaguer. So max response time again looks good. 99 percentile also looks good. We also had a graduation student that more or less did the same tests but with his own examples. And he saw that REST could handle around 600 users in his case, and remote actors could handle at least 1,000, and he estimated it could handle 3,300 users. So that would mean that if this is a production system with REST, you need like 5 or 6 machines to handle 3,300 users. With Akka, you just need 1 machine. So also from a business perspective, it would be a good way to use. So I mean, after these slides, I think it's easy, isn't it? But I went a bit further. Most of you probably know Spring Boot. So I also compared remote actors with Spring Boot, because it's a common framework. Lots of people nowadays are using Spring. It's, I can say, more mature, I think, than Akka, because Akka is a lot newer. So I was like, okay, let's see what's going on there. And yeah, that was a bit of a pity, because remote actors lost. And I was like, okay, how am I going to do a good talk now to convince people to use remote actors, because they're losing? That was a bit of a shame. But the nice thing was that if we look at the max response time, so the first one was the mean response time, but the max response times with remote actors, they're a lot more stable, and especially under higher load, they still work properly. And Spring Boot, I mean, the response times are like 3 times as much or 2 times as much. So we see that under higher load, still remote actors, they have a more stable max response time. So maybe the average is not as good, but the max response time is a lot better. And that means the 99 percentile is also better. So of course, it depends on your case. I've had that remark before, like, okay, you cannot say this directly, like, okay, remote actors wins. It's depending on what you're building, of course, but I think it shows that remote actors can be a good alternative to REST, depending on, of course, the scenario that you're implementing. Of course, we also had some challenges. This is not my house, unfortunately, because probably I would have good insurance if I had a house like that. But so, okay, Raspberry Pi's IoT hardware, it's getting quicker and quicker. So you can do Java on it, Scala on it, everything. But we still use the Raspberry Pi A+, and that has 256 megabytes of RAM. And with the camera and the software for it, the RFID, the other software we're running on it with Scala and Akka, we reached the limits of the 256 megabytes. So if you want to do more advanced stuff, either buy a bigger Raspberry Pi or a real server. Yeah, I've had some broken Raspberry Pis as well. If you ever buy a Raspberry Pi A+ and you want to put a USB connector in it, make sure that the pins are bent down. Normally you have pins that keep your USB device inside the connector. But the problem is with these pins with the A+, if you put something in it, it will bend backwards, and that's the end of your Raspberry Pi. And it only happens with thicker USB devices. like a USB dongle that I had that cost me 3 Raspberry Pi A+s. So one advice, use a screwdriver and just bend the pins down and then you can just use it. Slight disadvantage of the Lego trains for me was that they're really picky for batteries. So using rechargeable batteries didn't really work. So sometimes it worked, sometimes not. So I ended up just using normal batteries, which isn't really environmental friendly. Yeah, like I said, RFID, it can be a bit tricky if you go too fast. Then you need to, or want to do it on high speed, you need to have a better solution or a more expensive RFID set. Wi-Fi issues, I couldn't put this one on a Lego train. But I also looked at using the 5 gigahertz Wi-Fi dongles. But support for that on Raspberry Pi is almost non-existent. You have to more or less build it yourself, the support for it. So in the end, we decided to just keep the normal dongles because they work out of the box. So it's not really plug and play. And you have really a lot of options. When we started, I really like Docker. So I was like, OK, we build it in Docker immediately and just deploy it directly. But the strange thing was that Raspbian, which is more or less the default operating system for Raspberry Pi, didn't have proper Docker support at that time. You had to cross-compile stuff and everything, and I already spent more time than I wanted, so I was like, okay, let's not do it. But Arch Linux, which is another Linux distribution for the Raspberry Pi, had built-in support for Docker already. I had it up and running without the trains a couple of months before already. So it's really searching for the right combination. I couldn't use Arch Linux in the end because all the infrared stuff I was using and the modules that were written for the other devices were all specifically for Raspbian. So it's a bit choosing between two evils and choosing a solution that will cost you as less time as possible. And there is a lot of documentation. I had documentation about how to wire the infrared transmitter. So I used that, and then it was like, oh, it smells funny, and why is it so warm? And yeah, that was the end of my infrared transmitter. Apparently the documentation was wrong, or I don't know, whatever. Yeah, and what I said, children with Lego is cool, but if they're too small, it's quite a challenge to make sure they don't break it off. But main challenge was probably time. It's fun to play with this, but yeah, a lot of people have asked me how much time did it cost you to build stuff like this? And I don't know, but it's really a lot, and I probably won't count it because then my wife will probably get really angry with me. But it's fun, and I liked it a lot more than just building some Hello World examples or something else. It just keeps you excited, and you can just keep on adding hardware, and that was one of the fun things for me as well. I've mainly played with software for the last couple of years, and this was a chance for me to, again, use some hardware, use some different sensors. And you can keep on adding sensors on this. You could use proximity sensors to try and do collision detection and stuff like that. So it's almost endless fun, if you have endless time, of course. So for the conclusion, yeah, we could run Java, Akka, everything, it ran fine on it. So we were quite happy with that. We had a lot of fun, and as we can see in the room here, most people are quite excited with it, and it's a nice example. It brings you to places like here, so it can all advise you, find a nice project to play with in your spare time, and maybe you end up at all kinds of conferences as well. So it has all kinds of advantages, but I think there is one big advantage which maybe you already seen it at the beginning if you were here early, but I'll play it nonetheless. Are there any questions in between? Oh, yeah.
Did you investigate why the performance difference between REST and remote act as well?
Okay, so the question is what the reason was that remote actors performed better than REST or the other way around? Yeah, it was quite simple. With remote actors, we saw that the resource consumption was a lot less. So CPU consumption was a lot less than with REST. REST is doing a lot of overhead more or less in that direction, and Akka is much better in concurrency without using the same amount of resources. So that's basically the conclusion that we had. I'm sorry, it's not a English beer, but Any other questions? Then thank you all for coming and enjoy the rest of the conference.